Good morning. Today's the topic is GIS based suitability analysis for master plan preparation. And a master plan is an important legal instrument for spatial planning of urban settlements. They intend to guide and regulate the urban development in a planned manner. And these plans are prepared for existing and new or for expanding existing settlements. So preparation of master plans with GIS technology intervention will fasten the process of preparing base map and increase accuracy. The digital format will also facilitate interdepartmental coordination of services among 9 departments. So here what we are trying to study is the benefits of the master plan, and especially how GIS and remote sensing can help in master plan preparation. Now the second slide is the formulation of GIS based master plan for Amrut cities. So the objectives are to develop geo-referenced. So geo-referenced means maps which are showing the location on the surface of the earth, maybe lat long, or it may be a UTM projection. So we call them geo-referenced. That means they are referenced with respect to the earth surface. And land use maps using geographical information system for 500 cities that are selected as Amrut city. So what is land use? Land use map is a map that shows the human activities that are associated with different clusters or different parcels of land. What is the use going on? It may be residential, commercial, industrial, and like this. So it basically depicts the human activity going on in a parcel of land. Now, what are the components of this? So the first component is we have to generate a base map. A base map is basically a skeleton map. It shows the major rivers, roads, geographical features, rivers, and then onto this skeleton map, which we sometimes call as a base map, or some authors also call it as a footprint map. Then on this base map, we transfer various themes like road network map, water bodies map, land use map, it may be cost of the land, drainage map. So there are various thematic maps because they show a particular theme. So on this base map, we transfer various thematic maps, and these thematic maps plus along with some socio-economic maps like the distribution of population density, the level of facilities, both physical and social infrastructure. Physical means you can show the water supply, sewerage, electricity, all those things. And social, maybe the location of schools, hospitals, post office, like this parks. So what we do, first we generate a base map that provides basically a skeleton onto which we can transfer various themes, like as I discussed, land use map, all those maps. And these physical and social maps, which are then transferred onto a base map, they constitute what is called as a urban database. So in Amrut, we are creating this digital urban database at a scale of 1 is to 4,000. Why we have chosen 4,000 is because this scale matches the scale of the cadastral maps. Cadastral maps are maps that show the ownership of land. Sometimes we call them as Khasra Khatwani maps also, Sajra maps. So in order to ensure that whatever we are planning that matches with the cadastral maps, we are generating this Amrut database at a scale of 1 is to 4,000. And this database is basically in a digital form, so easily we can edit it in a digital format, transfer it from one place to another, and this safekeeping of the map is also not a problem. Then using this urban database consisting of various thematic maps at a scale of 1 is to 4,000 in a GIS environment, we are generating the master plan. So master plan is nothing but it is a document which shows or which provides a reference for future growth of a city. See, an urban planner, he has to take a decision regarding the future growth of a city. So master plan is a document. It's of course a legal document, and it provides us a reference or a framework within which we can take future planning decisions. So it provides a reference framework for the urban planning authorities. So this is the definition of master plan. Master plans were also prepared earlier when there was not much of digital things into use. They were not the convention. But now, if we take this GIS, this digital thing into picture, then we can generate master plans more easily, more effectively, and transmission of this master plans and safekeeping, record keeping is also easy. So these are the advantage of generating a GIS-based master plan. Plus, we can also generate different scenarios, what if scenarios. If you do growth like this, how it will grow. If we make a master plan like this, what will happen, how the city will grow. So this scenario-based generation can be done very fast and accurately in a GIS environment. So these are the advantages of making a GIS-based master plan in comparison to the conventional way of making a master plan. Now, what is the process of GIS master plan formulation? Moving. So the process of formulation of GIS master plan is, first of all, we demarcate a planning area. So the town planning authorities or basically the urban development department, it will demarcate an area around the city which it considers to be the future urbanizable area. So that is called as a mapping area, or you can say it is a planning area. So that is an area which is having very lot of dependency in terms of employment, socio-economic on the main city. So we consider it to be a future urbanizable area, and that area is demarcated by the planning authorities, and we generate the master plan for the entire area, because we cannot plan for the city in isolation. We have to plan for the city and its surrounding environments also. So the first thing is we demarcate a planning area. Secondly, we acquire the satellite data of the respective area, right? Then we do a GPS survey. The GPS survey is done. So in order to find exact XY coordinates of some reference points, because using these reference points only, we will accurately register our master plan with respect to the ground. So whatever the road we say that comes exactly in the place where it is on the earth. So we first collect GPS survey. GPS is nothing but global positioning system. So in this, we mark the X, Y, and Y coordinates of some points on the ground very accurately. So you can use a differential. Normally we are going for a differential GPS. After the survey is done, then using the points collected in the survey, we georeference the satellite data. Okay. Okay, just let me see. The pointer is working. Yeah. So what we do is, after we have done this GPS survey, then this data, satellite data which we have acquired, this data, so it is something like this. We have a satellite data like this, and these are the location of the GPS points that we have collected during the survey. Then using this, because we know the exact X and Y coordinate of these points, using this X and Y coordinates, we georeference this satellite data. So now this, all the features, may be a road or it may be a house, they will come at exact same location on the Earth surface. So the map will show their exact location on the Earth surface, maybe in terms of lat long, that means latitude or longitude, or let me be a lat long, or it may be a any other projection. It may be a UTM also. So after we have done georeference, what we do is we try to digitize or basically delineate these points on the map. Like this is the house outline of the house. This is the road. This may be a water body formed like this. So, and then we see the topology of these things also. Topology means whether the spatial relationship between these features are exactly shown on the map. That means, is the map showing these two features to be adjacent to each other? Is the road adjacent to the river? Is the river at the given distance from the house or this building? So now that we see, first we have taken remote sensing data, then we have exactly given it the reference so that each point on the map shows the same location on the Earth surface. That is called as georeferencing. After georeferencing, we delineate various features on the map, and we then try to see whether these features are exactly shown, whether the relationship that is existing on the ground between the features, that is neighborhood, this house is the neighborhood of this building, this is at this much distance from this. So this topology is exactly encoded in the map or not. So that is called as topology building. So after topology building, what we get is, we get a map like this, which shows us the location of the houses, buildings, it may be house or a building, the location of the roads, and maybe the location of the water bodies, like this. Okay. Then after we have done, then we go to the ground and we see, we try to verify with actually what we have demarcated on the map is existing on the ground, because it sometimes happens some features we are not able to identify on the map, on the satellite imagery. So sometimes we may miss some features. So then we try to find out how accurate is the map that we have generated. That is called as ground truthing. Okay, so after this, we also add some data from various departments. Like it may say like this is the you may say this is a hospital. You may say or this is the cost of land is this much rupees here. It means some data may be like this, or this building is this much age, or this building can accommodate so many people. So like this data, we further add to this map. That is called a value addition for line department. So some information we get and we add. Finally, so what we have done, we have given that first we have made sure by georeferencing that each point which we are showing on the map is having accurate x and y coordinates with respect to the Earth surface. So it is showing the location accurately. Then we say whatever features we have mapped on the Earth, on the map which we are derived from remote sensing, the relationship between the topology is correct or not. Then using some data provided by the various departments, line departments, we add some more information to the features which we have delineated on the satellite imaging. After we have done this, we go for ground truthing to find out whether what we have done. And after we are satisfied, we go for a quality check and vetting, basically that can be done by a third party also. So after you get basically this type of a quality control check, you can say. It's type of a QC checking, we say. Quality control we go, okay? So it's a QC we go. After the QC, you see the done. After the QC is done, then we can say our GIS map is ready or our GIS digital database is ready. So like this, we generate various thematic map showing the location of roads, map showing the location of water bodies, map showing the location of various land uses, of parks. It's like this, different thematic map showing the cost of land, but for the cost of land, we require data from the line departments also. So all these maps, then we make thematic maps. Okay. So this now we say thematic maps. As I told you, we can also add some primary and secondary data. Some data you can get from the line departments, some data you can collect from survey. So when you collect all these data, finally what you get is called as a thematic map generation. Okay. Now we analyze these maps in a GIS environment for identification of issues and potential. Like if you want to make a master plan for a city, what are the problems? What are the problems basically? What are the problems that are being faced in the city? It may be unplanned development, or it may be, you say, pollution may be a problem, or encroachment of water bodies can be a problem. So after we first try to analyze the problem, and then we say what are the future potential of the area. Can we develop this area as a tourism center? Can we develop this area as an industrial center? So you see, we have to plan for next 15 to 20 years. So first we analyze what are the problems in the city. Why these problems are there? It may be because of what do you say, a particular growth strategy that we are following, we are having this problem. A lot of reasons can be there. So first we do identification of problems, and then we identify what are the various potentials of the city. Potential means, can it develop as a tourism city, or can it develop as an industrial city like this? Or it may be a service center we can develop. So these, what are the potentials? Then we project, like based on the existing problem and the potential, what are the future requirement of, you can say, water or electricity, maybe roads can be problem. What are the future roads? What are the future infrastructure that is required in terms of what schools and this? Then we do what is called as a projected requirement. And after, you see, now you see up till here we are having a what is called as a digital database is ready. So a GIS based digital database, first we generate a digital based database. After our database is ready, we try to identify what are the problems. Okay, see, your database is ready, then you analyze this database in a digital environment, and you try to find out what are the existing issues, what are the existing potentials, and based on these two, you try to go for the requirements. So now, and then you try to formulate a policy. So this, up till this part, it was basically development of a database. Here we try to identify the problems, the potential, and based on this potential and issues, what will be our future requirement and how should we go about achieving this requirements. So here it is basically more of policy and future prediction. Now we have the database. Here we see we have the database is ready. The future projections are ready. Here basically we go for what is called as a development of the master plan. So this is the third stage, you see. So entire process you can divide into two stages, three stages. First stage is development of a database. Second thing is based on the database, existing database, you identify the problems and the future growth direction, policy you want. And third thing is you combine all first and two results based on the database, requirement, future policy, you make a, here, first you have done database, then you have done policy, and now based on these two, you are trying to identify what will be your future plan. So this is called future plan. So as was mentioned earlier also, you can develop different proposals of the master plan. You see, you can have 2 or 3 development policies. You say, if we do this policy, how we should make the master plan? If we follow this policy, what should be your master plan? So this kind of scenario generation is very fast in a GIS. In a GIS, this kind of thing is very fast. This is the advantage of using a GIS-based approach for making a master plan. Okay, you can generate different scenarios very fast. That is the advantage of going for a GIS-based master plan approach. So, and this is broadly how what are the steps involved in formulation of a master plan. Of course, the steps are same, but previously what you want to do is stage 1 was done manually, so it took a lot of time and labor also. But now using modern techniques and tools like remote sensing and GIS, this stage can be done very effectively and very accurately and very fast. And secondly, here also in generation of master plan, earlier we were using by manually also, but now in a GIS environment, this process is also now very fast. Okay, so this is the advantage of using a GIS based master plan. Okay, now here I will tell you what you see now is this is a Dehradun master plan that has been made for year 2025. So master plan, it shows you what are the existing areas, what is the existing built up, and what we plan to do in the new proposed areas. What would be our land uses, what will be our population density, which areas will be left as a green belt. So these all things we are doing we can do in a GIS based environment. But our end thing will be basically a master plan. You see, either you do by a manual way as we are doing earlier conventional way, or you do a GIS based approach. It will, the end product is we want a master plan which shows us what is the future growth direction of the city. So this also provides a framework for the urban planning bodies for taking future decisions. Now, what are the classification systems? You see, land use is a very important component in any master plan. So normally, what are the various land uses classification which we should follow in a master plan? So it is residential. Residential can be divided into residential, medium density, low density, or it can be minimum or it can be a low density. So it can be residential low, residential medium, high and high. So first is residential. Second thing is commercial, whether it is retail or wholesale, as I told you. Sometimes in residential areas, we allow some commercial activities so that they serve as facilities for the neighborhood level. While bulk, normally we provide a different area where we can have loading and unloading facilities also. What are the official? That is, it's a government or it's others. The agriculture, the forest. Now the forest, sometimes we include the gardens, the tea gardens. Of course, the forest, reserve forests are there. Of course, this is basically an institute very specific for our area. FRI. What are the utilities? Like it can be water supply, electric supply, gas go down, sewage plants, solid waste, milk dairy, slaughterhouses, colleges, different kind of colleges, high school, inter college, degree college, ITIs. Okay, so this is all education basically. The hospitals, veterinary hospital or normal hospital, telephone exchange, TV, fire brigade, police station, religious places. So these all are coming under utilities. And transportation, as I told you, what are the flyovers, elevated bridges, elevated sections, link roads, rail, railway station, bus stand, traffic station, local stand. You can also have airport also or port also sometimes if it is there. Then some restricted area, basically they are the strategic areas, the defense areas. Then we also have a heading under miscellaneous area, that is a recreation ground, the tourism point, tourist area, animal park, all these things are there, sports colleges, and then the water bodies, there's natural water bodies and artificial water bodies. So there is nothing like this is the template we have. We can have any type of classification system as per required for a study area. But normally I am just showing you one of the ways we can classify different land uses into different categories. Okay, so the prominent is basically it is a residential, commercial, industrial I have not shown, but it can be industrial also. Okay, industrial is also there. Okay, we can have industrial also. So residential, industrial, commercial, official, agriculture, forest, utilities, transportation, restricted areas, miscellaneous areas, and water bodies. This is one of the classification we can have, but this is not like the final one. You can follow as per your requirement. If there is no big industrial area in your study area, you can leave this. If it is there, you can include it. Similarly, tourism may not be that much important in a study area. You can may leave it, or you can have only one class. Instead of having this much classes, you can have only one class also. So like these things, you can generate a classification system. Okay. Now, see, the third thing is, how do we go about, you see, when you generate a master plan, it is more of it what is called as a multi-criteria evaluation technique. So here we have got different criterias, and these criteria we have to basically integrate into a common suitability map for future development. So this is called as a multi-criteria evaluation technique. So making a master plan is also sometimes a multi-criteria evaluation technique, right? So there are different approaches for following a multi-criteria evaluation technique. It can be a Boolean, it can be a weighted linear combination, it can be a ordered weighted average also, right? So if you follow, so there are different approaches. One is an approach. If you heard something about Boolean algebra, it is called as total risk averse, or it can be a OR approach. So OR means you are taking risk. If at least one of the criteria is filled, you say, okay, we can go through it. And there is something type of a C. If a particular land fulfills all the criteria, then only we will develop it for a land use, maybe residential only. So here it is totally risk averse approach, and here it is basically totally a risk taking approach. So normally what we do is we follow somewhere here, neither a full risk averse, neither a risk taking. So normally when we follow this multi-criteria technique, it is basically a trade-off between both of this. Neither it is fully risk averse, neither it is a risk taking approach. So here we are following somewhere in between, that is called as a multi-criteria evaluation technique. So I will discuss with you one case study we have done for Dehradun. So this is the basically what you say, the land use map of Dehradun, which we generated using remote sensing data in a GIS environment. So it shows you the agriculture land, the tea garden, the forest, the vacant, the village, the plant. So different land uses we have shown, and what you see these numbers, they are nothing but the coordinates. So what we have done is, first we have taken the remote sensing data, we have geo-referenced it, Georeference means we have given coordinates with respect to the Earth surface, and now here if you click any point here, it will show you the exact location on the Earth surface. So this is nothing but a location grid which we have imported, put on this top of this map, and this is a thematic map which shows you the different land uses in Dehradun. Okay, Dehradun city is located in Uttarakhand state of India. This map shows you the flood hazard map, like areas where we have no flood potential, areas we have very low flood, high flood, and these are basically the river water bodies. So this is the river that flows through our study area. These are the water bodies, rivers and streams. And then we have found out, because now urban flooding is also one of the biggest issues we face, and it also causes a lot of damage to both human life and property. So here we have tried to quantify, like we have tried to make a flood hazard map for our urban area, our city, and the surrounding areas. This is a geomorphological map, you see, because when we are making the various structure on the Earth surface, we should always also be familiar with the subsurface or the geomorphology of the area, because during hazards, the geomorphology also plays a very important role. So we have created three maps, you see. First is the land use map. Second is the areas which are prone to hazard or which are lying in a high flood and low flood. You will see that most of our areas, they lie in low and very high flood. Some areas along the rivers, you see here, this in red, they are only prone to high floods. But most of our areas lies in a low flood, or a city is basically here. Our city is here. Somewhere here we have the urban area. So this basically falls in a very low flood area, basically, or a low flood area. And some part is coming here into the very low flood also. So what, even then, we have taken hazard flood also as one of the factors when we are trying to select areas for future development of the city. Okay. Now this is, we have a geomorphology map. So you can see the different geomorphology, and most of the study area, this falls into basically the middle dune gravels. Okay, most of it falls into the middle dune gravels, as you can see from the map also. And secondly, here we also have some area. This is calling into the Dehradun fan gravels, right? That falls into the Dehradun fan gravels. The third thing is, for any urban area or any settlement, water is a very essential requirement. So here we have tried to make a map which shows you the groundwater map or the groundwater potential. And you see the most of the study area, it is falling in a good. Yeah. But you see these factors we have to see what we are trying to generate is, we are trying to generate different factors corresponding to different thematic maps, and then these thematic maps will integrate in a GIS environment using a GI, using a multi-criteria evaluation technique, and finally we can find out areas which are suitable for future development. So the same approach we can follow when we are going for a GIS based master plan. Only our scale at the time under the AMRU scheme will be at a scale of 1:4,000. So it will be a very high resolution map, a map showing the details, yeah, that we will be getting. So this is a water potential map. This map shows you the areas which are prone to soil erosion, right? So you see these areas where our planning area is there, somewhat it falls under unaffected area, and some of it falls into the moderate erosion areas. So these things we have to see, like we should not plan our structures areas which are having very high severe erosion. You see, here we can have recreational and some other type of uses because if you go for a heavy construction here, we make industries, or we go for a high density residential development in this area, then it may become a hazard and the risk may increase for the urban population. So here we are showing you like what are the different things we should keep in mind, especially with respect to the hazards which endanger both human property and life while making a master plan of a area. So this is the map which shows you the soil erosion hazard map. This is a contour map. I think so. This just shows you the height. So this is basically just hiding here. So this is one of the map. So this is the basically the distance map. Basically, okay, the distance from the major road. You see, these are the roads you can say, and this shows the distance. And sorry, this is just not going. But if you can skip from it, maybe we can. Okay, and this basically is a road network map I showed you. Accessibility is a very important parameter in today which guides urban development. So what you can do is you can generate a road network map, and then you can find out the distance from the different kind of roads. So this tells you the how accessibility will affect your growth patterns. Okay. See, as you have seen, normally in urban areas, what we have growth occurs within a certain buffer of the main roads. So most of our growth is road network driven. So what we have to also ensure is that our development should not follow a ribbon development. Otherwise, what happens if your growth is like a ribbon, it is just like the main road networks, then providing infrastructure facility, especially your water supply. You see, water supply, sewage, electricity is very costly because the development will be like this, and in between there will be vacant areas. So you see what happens. First of all, we are not having adequate utilization of the land, and secondly, provision of infrastructure facilities like water supply, sewage will also be very expensive. So we have to ensure that our development, urban development, is not ribbon, but in fact it should be just like this. It should be bulk like this. It should be compact, so we don't have wastage of land like this. And secondly, accessibility to various facilities will be less, and the cost of providing various facilities also will be less. Okay, so that is why we are also taking distance from road as one of the factors when we are making a site suitability analysis. We try to do then, especially for in urban areas. Then this distance from road is also very important factor which influences the growth pattern. This is a slope map. Of course, you see, what we want is that our development should not take place in very steep slopes, because then cost of cut and fill operations, and again I told you, cost of providing roads and infrastructure facilities also increases. So normally we should try to keep our development in a running slope basically, or a gradient should be gentle. Okay, so slope is also one of the important factors. So here first we have taken a digital elevation model which you can take from SRTM or any available sources, and from there in a GIS you can easily generate a slope map. Now what we have done till now is we have made various thematic maps. Okay, we have made various thematic maps. We have made various thematic maps. Now we want to integrate or some of these maps so that we can find the suitable sites. That is our problem. Now what we have done here is, here in a GIS, since these maps are made in a GIS, so here in a GIS environment and using multi-criteria evaluation technique, that is MCE, a multi-criteria evaluation technique, we have what we have done, we have summed this map to show you which is the area which is very suitable for future. This is what basically how we can use GIS for making site suitability or also for making master plan, which shows us which future areas are suitable for urban. Right? This is how we go. So till now what we have covered is this part. What is the various thematic map. Now we are trying to do how we have combined these things into a single map. So what we have told is that how we have done this is we have decided like areas which are barren, vacant, or having low agriculture productivity. There we say our future growth will take place, because we have to preserve the existing high productivity agriculture areas. Fertile agriculture lands also have to be protected. We cannot go about converting these lands into built-up area, because once they are converted into built-up area, then they will be lost permanently. Okay. Second is the slope or the gradient should be less than 15%. As I told you, if we have a development on a very high gradient, then it is not safe. Secondly, the cost of development is also very high. The third thing is, as we showed in the flood hazard map, our area should lie in a very low or low prone, hazard prone area, considering in the frequent urban flooding which we have seen in various parts of the country, and the damage it causes both to the human property and human life also. Secondly, the very urgent requirement is the groundwater. The groundwater should be availability should be moderate to very good, because we have to cater to the urban population. And the normally in urban area we have got a high population density, so water availability is there. As you must have seen, a red in summers in many major cities, water supply is a critical issue. Then the distance from road should be less than 1500 meters, because accessibility is important. Third thing is the geomorphology. In our case, we are following this geomorphology, but you can choose appropriate geomorphology for a study area. Fourth, the severe soil erosion should be, the very severely eroded areas should be left, because they are not suitable for human development or habitation. And the area minimum should be more than 10 hectares. You see, if you are very satisfying all these criteria, a very small parcel of land is available, then also it is not of much use, because if you want to develop a new urban habitation there, then the area should minimum be 10 hectares. Okay, a very small parcel of land will not serve a purpose, because we are not planning for a single house or a single family accommodation. We are basically trying to find out which areas are suitable for future urban growth. So that area constraint is also there. So what we have done is, we have chosen the thematic maps. We have chosen various criteria which have to be fulfilled. And then in a GIS, we overlay these maps and try to find out which areas are there which are satisfying our query. And one of the queries is the aerial requirement also. The area should be nothing. So one thing is, as I told you, either we can have a totally risk averse approach, that is an AND approach, criteria which fulfills areas which fulfill all of these requirements will only be developed. That is called as a AND approach, or a totally risk averse approach. Second thing is, we can have a risk taking approach, that is called as a OR. If a parcel of land or a particular area, it satisfies even 2 or 3 criteria, then it may be selected. So that is called as a risk taking approach, okay, or a OR approach. So that's why you see, first I tried to tell you is, should we have a totally risk averse approach or a risk taking approach, or an OR approach or an AND approach. And thirdly, we can have something in the middle. If you remember, I showed you this decision space also. This can be an AND approach. Here we can have an OR approach. Some issue is there. We can have an OR approach, or we can have somewhere in the middle here also. That is neither total risk taking nor the total risk. And net risk. So normally in MC, what we do is multi-criteria analysis. We normally go for this kind of thing. We can go somewhere in the middle, basically, neither on the both extremes. Okay. So as I told you, in Boolean approach, the factors are reduced to simple constraint. That is, we either go for a yes or no approach. The final map of suitability for urban development is the product of the AND operation. Or that means if a location is not suitable for any criteria, it will not be suitable on the final map. Or we can go for OR approach. This I told you, OR approach somewhere here, which is too much of a risk taking. So that's why again I'm mentioning we should somewhere finally settle down somewhere in the middle. Neither too much risk taking, neither too much risk averse approach. So first thing is, these are the criteria we have followed. It is a land use, a slope map, a erosion map, a road buffer map, okay, groundwater, geomorphology and flood. And okay, I think we have this. The results of the issue now. Yes. So here, what we have done is we have taken the AND operator. You see. So we have used a AND operator. So any parcel of land should fulfill all these criteria. Okay, and we have taken a AND operator. Okay, and then the result is something like this. Okay, so we say these are the parcels of land using AND approach, we can say, and this much area we can get like this. Okay. But what we normally do is we don't follow this, we follow somewhere in the between. So here weighted linear combination allows us the full potential of factors as continuous surface of suitability. And but what we do is we give various weights to the different factors. Okay, and it is neither too extremely risk averse, neither it is too much risk taking. Okay. And all factors are allowed a trade-off. So any factor can compensate for any other according to its factor weight. One thing is we say all factors are equally important. You add these two factors together and what we get is called as a suitability map. Or we can give various weights to these factors. Okay, and then we add them up. So that is called as a weighted linear combination. Weighted linear combination map. So here what we do is there is a method given by SETI that is called as pair-based comparison method, and here we give different relative weights to the factors based on their importance. So this is called as a weighted linear combination map. So in MC, if you are following a WLC approach, that means you are not following an AND or extreme approach. When you follow the middle approach, what we do is we give different weights to the factors based on their importance, right? Like whether this factor is important or this factor is important. And then to calculate the weights, we usually follow a SETI method. So in SETI method, what we have a pairwise comparison of different factors. Like if we say flood hazard is as important as slope, then both will be given 1:1. So here we have a ranking from 1:9. Okay. If one factor is very important, it is given 9. respect to other. Less important 7, then 5, then 3. And if you give 1, that means both factors are more equally important. And the inverse of this is this. So if we say, you see, now this means slope is, this land is very much more important, 3 times more important compared to slope, right? Similarly, erosion is, now this is a, erosion is very less important compared to the flood hazard. So this what we say is, and groundwater is 2 times important compared to erosion. And this means land use is 1/3 less important compared to flows. So if it is 2, 2, 2, it means groundwater is 2 times important compared to flood hazard. Groundwater is 2 times important compared to erosion hazard, right? And groundwater is less important compared to land use. So what we do is, we all these factors which we have taken in the earlier, which I shown you earlier, we do a pairwise comparison of these factors using a SETI scale, where we do a comparison on a scale of 1:9. Okay, so that first we do a pairwise comparison, then we calculate the eigenvector and eigenvalues of this matrix, and the principal eigenvector is called as the weight matrix. So this weight matrix is nothing but the principal eigenvector. Okay, so this matrix is called as the decision matrix or the SETI method, SETI's matrix, and then we do a pairwise comparison of this. I told you a pairwise comparison of this factor is done, and after we generate this comparison matrix, then we calculate the principal eigenvector of this vector of this matrix, and the principal eigenvector gives us the weight. Like, what is the weights in terms of importance that is given to different factors, right? And find out whether our weights which we have got are consistent or not. We calculate a consistency ratio. So a consistency ratio should be less than 0.1. If it is less than 0.1, we say our weights are consistent. If it is more than 0.1, then we say the weights which you assign, they are not consistent, and again we assign the weights, and this process is carried out iteratively until our consistency ratio comes below 0.1. Once it is below 0.1, then we can say like our weights are okay and we can go ahead. Okay, so this is a very simple method, but the method we follow is called as SETI's method or SETI's pairwise comparison method. So either there are some softwares available, you can use them, or you can carry this analysis easily in Excel sheet also, because what we are doing here is we are simply calculating the eigenvectors. Okay. So here what we have done is, as I told you earlier, this is the weights we have given. So each map we multiply with the weight. So soil erosion map is multiplied by 0.137. Standard is multiplied by this. This is multiplied by this. So what we are doing is, we are doing, suppose I say this is map 1, this is map 2, this is map 3, this is map 4. Then what I do is map 1 into 0.1327 plus map 2, this 2 means map 2, okay, into 0.233 plus map 3 into 0.1114. This figure is basically coming from here, the weights which we have calculated using SETI method for each factor. And like this we keep on doing. Suppose this is 4, then this comes out to be 5, this is 6, and this is 7. So finally we do map 7 into 0.1393. So this what we're doing, this is called as WLC, that is means weighted linear combination. Okay, this is called as a weighted linear combination, because what we are doing, each map, we are first this map is map 1, we are multiplying by its weights, and then we are doing a linear summation of this. So mathematically you can express it, sorry, my summation comes out like this: W into I, Wi into Xi, okay, for all values of I. Means I value varies from 1 to 7, how many maps are there. So what we are doing is, we are basically doing a weighted linear combination. First, we are multiplying the various maps with their respective weights, and then we are adding them. So this is called as a weighted linear combination. Then we also apply a constraint, like any area which is having too much of slope or coming into a restricted area, and the land should be more than 10 hectares. So we may get a map satisfying this. Out of this, we basically filter out areas which are satisfying these conditions, like areas which are not satisfying these conditions, sorry, not satisfying. Areas less than 10 hectare, it is situated. Areas in a very steep slope, or areas which is in a restricted area, maybe a defense area. So whichever things are not satisfying these conditions, these things are now filtered out, and what you finally get is basically a map like this, which is called as a site suitability map using a multi-criteria WLC approach. Okay, so what happens? Our area figures also go up. If you see, while we were having an approach, you see our area was only 9827 only 9827 area was available, and these were the different areas. Okay, but when we have used a WLC approach, our area has increased. See, and if you follow a OR approach, then your area will be more. So you see, as I told you, we should, if this is a decision space, so this is an AND approach, this is a OR approach. What using VLC, we are somewhere trying to sit here. So our area will be between this and this. This will be the minimum, and this will be the maximum. So our area will be somewhere between this thing. So when we follow a weighted linear approach, we finally try to settle somewhere in between. So this is the advantage. The thing is, you see, when you follow a weighted linear approach, you try to settle somewhere in between, and you can also incorporate various human decisions things in the between. So the MC procedure used in the previous two methods lies along a continuum of AND or. The Boolean methods, basically AND or both, they are called as Boolean operators. I think you must have studied somewhere in your 12th class, maybe I think, or later in your bachelor's also. Boolean operators, that's called AND or operators. They give access to the extremes, while the weighted linear combinations somewhere comes in the middle. So at both extremes of the continuum or the decision space, trade-off was not possible. But in the middle, there is full trade-off. You can basically give some more importance to some factors, some importance to less factors, and then you can do what is called as a trade-off. So OWA, that is called as the ordered weighted average, it gives us the control over the position of MC along the risk and trade-off axis. Okay. So here what we do is, the control over the risk and trade-off is made possible through a set of ordered weights for different rank order positions of factors at every location. So we see what we are trying to do is, Broadly telling you, either you go to the two extremes, or if you don't want to the two extremes, you basically give different weightages. So by giving different weightages, you are trying to move along the axis in the decision space. So you can position yourself at different spaces in the decision space. Okay. So this is the advantage of following this multi-criteria or different weightages approach. So similarly, if you want to make master planning, so instead of following a sieve analysis or type of a Boolean operation, like it should either fulfill all or it will not be accepted, you can go for a weighted approach. You see, sometimes in our everyday life also, we follow a weighted approach. You see, if you want to buy a particular thing, you don't cost, quality of the product, many criteria may be there. So we don't say a criteria which fulfills all should be there. We try to basically do kind of a compromise solution. Basically, we go like we are not going for the extremes, but we try to give different weights to different criteria which we have for buying a particular thing, and then we say the thing that satisfies our most of the criteria, or you try to give different weightages to the different criteria, and then in somewhere means you come to a decision. Same thing we have tried to do here. We are not going to the extremes. You see. So you see, again I'm telling you, we are not trying to go to the extremes, but we are trying to move somewhere in this decision space. In this decision space, we try to move. Okay. So, and then we try to take a decision. So this entire process of multi-criteria analysis is, we are not going to the extremes, but we are somewhere trying to shift or move in this decision space based how much risk we want to take or how much risk we don't want to take. Okay, now. So this has the effect of being factors based on the rank from minimum to maximum for each location, right? The relative skew towards minimum or maximum of the order weights controls the level of risk in the evaluation, right? So this is the advantage we go. So first thing is, see, if you try to follow a low risk, no trade-off, then we settle somewhere here. Then this kind of things we will get. Area will also be there. So you see, instead of this, we have moved in, we are not in the middle also. We are basically trying to move here by following what is called as a rank system, okay, or what is called as the order weight. So we are having low risk. You see here, we are having low risk and no trade-off, okay. Then second thing could be, these are the different ranks and we give different weights, order weights. So now we have moved here. So this is called high level of risk, but we have some trade-off. So first we are here, then middle and this. In middle, what we do is we assign equal weights to all the factors. That is why we land in the middle. But you can move here also, you can move here also, right? This is the middle, I told you. Somewhere in the middle, where you can say, we say average level of risk, no trade-off. You see, we are having only one factor, so there is no trade-off. Here, but the level risk is low. Okay, but here you see the risk is more. Okay, but here we have got a trade-off. Some trade-off is there. Okay, here we have got no trade-off because all other is zero. Then here is, if you give this, you see, your risk is, we have some trade-off, but the risk is less because we settle for somewhere here. Okay. So you see, if you take different approaches, the area and the suitability will be this. So in a final, you can say Boolean reduces our factors to simple constraints that represent hard decisions. WLC allows full trade among factors. And O order weighted average provides risk between control between risk and trade-off through a set of order weights. You see here, order weights. So either you can take all weights to be one, then you come somewhere in the middle, that is called WLC, or you give order weights and then you try to control how much risk you can take. So this is basically how we go about taking decisions when we are basically working in a multi-criteria environment. We have got different. So when we make a master plan, also we have got a multi-criteria type of a problem. We have different factors and we have to decide the optimum results. So there are three phases: Boolean, WLC, OWA. So this is just to give you idea how we go about making decisions, especially when we have got different criteria. And here GIS provides us with basically a environment where we can handle this data and do this kind of modeling. So this is all basically how this summarizes our topic which we started, like GIS based suitability analysis for master formulation. So this is all from my side. If you have any queries, I think you can post it and discuss. So thank you for your attention. And